everyone. Thanks for joining today's talk. This is the first lecture of Motivic Homotopy theory by Professor Chetan Tukaram Balwe. We'll start now. Yeah, up to you.
Okay. So object we are studying, and then maybe we can I can conclude with possibly reading suggestions about what you might want to read, so that you can follow the literature. In this talk, I mean, I've been told that I shouldn't assume what a model category is. So I will not necessarily define a model category explicitly, but I will say a few things motivating what it is and how it is going to be used. So I mean, in this lecture, I mean, I had thought I will define the even homotopy category and talk about some results, but actually it will not really come to that. I think I'll barely finish just defining the object, but it will still require some explanation and some motivation, which we can carry on in the next talk. So so let us see what is the motivation behind what we are trying to do. So we are trying to study, we study topological spaces using the notion of homotopy. So why do we do that firstly? So I mean, speaking very simple-mindedly, our objective would be to which is too big a task. And so then we compromise and say, okay, we'll classify them up to homotopy equivalence. And so the thing is that does bear some success, and so we want to create an analog of this in algebraic geometry. And but of course, in algebraic geometry, even if you are doing this over the real numbers or complex numbers, the unit interval which would be used to define homotopies, that's not an algebraic object, right? It's not an object in algebraic geometry. So you have to analog for that. So the analog that we use is the affine line A1. So the affine line, so the endpoints are going to be the points 0 and 1 on the affine line, right? But you're going to use the entire line and not just the interval 0, 1. But I mean, of course, this is not going to be done just over R or the complex numbers. So it is over a more general class of fields. So why might we want to do this? So the reason is that many of the functors that one studies in algebraic geometry, they are what one might call as A1 invariant. So we say that a functor is A1 invariant if or homotopy invariant if see, the thing is that you have for any variety X or any X, you have the projection map from X cross A1 to X. Okay, this is just the projection onto the first factor. So now if F is a functor on the category of schemes, so I don't necessarily need the full category of schemes. I mean, if I say full category, F, then I will say that F is A1 invariant or homotopy invariant if the induced morphism from F of X cross A1 to F of X, this is an isomorphism. So this is a fairly natural way to define this. Of course, the way I have framed this, I'm taking F to be a covariant functor. But if it were contravariant also, it will make sense. It's just that the arrow gets reversed, right? That's all. Okay, and now, so what are some examples of this? So some common examples would be, for example, Chow groups. These are A1 invariant. Étale cohomology in the appropriate setting would be A1 invariant. Like, for example, if you're considering this on, I mean, you're looking at Étale cohomology with coefficients in a torsion sheaf where with the torsion of which is co-prime to the characteristic of K, then this happens to be A1 invariant. Also, algebraic K theory, I believe you are going to be running some workshops on. So if you look at this over regular Noetherian separated schemes, this will also be even invariant. So, I mean, my point is that simply that these things, even invariant functors occur naturally. And that is why this thing is interesting. And the similar thing happens in topology also, that in topology also, the functors that we are studying, in a way, it's kind of built to be that way, that cohomology and homology and variant. It makes sense to look at this. So then what do we do? So in topology, what we do is we consider the homotopy category, which means that what we are doing is, this is, you basically localize with respect to a certain class of morphisms. So we would like, so whatever category of schemes we are using, we would like to look morphisms of the form x cross a1 to x. These should be morphisms. This is what we want. And in principle, there is, I mean, I could just say that and stop. But the point is that when you localize categories, the localization of a category with respect to a class of morphisms, it's very easy to define abstractly, right? So the thing is that if you place some restrictions on the size of the category and so on, I mean, if some set theoretic aspects are taken care of, conceptually, it's a very simple thing. That if I take, basically, I will not change the class of objects, right? The objects will remain the same. And what I do is I take two objects, X and Y, then the morphisms between them will be given by a zigzag. So basically in the original category, you move along a zigzag of arrows. By zigzag, I mean that some arrows you follow in the right direction, but the arrows that you mean to invert, you can follow them in the reverse direction, right? So that kind of a thing you have. And then using this, you can define, so this would be a general morphism in the localization. And one can make sense of this, and it's fine, right? So happening there, but the problem is that this is very hard to work with, right? I mean, so what do I mean by hard to work? So what you really want is that given objects in the localization, so which means basically objects in the original, in the localization. So the thing is that because you are not, you are following a zigzag, you may be creating entirely new morphisms, right? Which are not represented by a morphism in the original category. So if you take two objects in the original category and a morphism between them, that's going to give you a morphism in the new category also, right? But there may be entirely new morphisms which are not represented by anything that you have in the original category. So that is what creates some problems. And so we need some extra mechanism to be able to calculate the sets of morphisms in the localization. So one familiar object which you may have seen is the calculus of fractions, right? So you assume that the morphisms that you are localizing, they satisfy certain properties which which remind you of fractions. Then you can describe things in a certain way. This would be particular. I mean, I'm sure those of you who have seen derived categories and so on, then this thing is used there. But another mechanism for this is the notion of a model category. So as I said, I will not explicitly define a model category because I think that kind of defeats the purpose of having a talk like this, because you can read the definition anywhere. But I just want to motivate a little bit. So I will just talk a little bit about what we do in topology. Okay. So again, I may this discussion also about being inspired from topology. This will also be kind of incomplete. We will keep returning to the topological example in a later lecture also. But let's just see what we do in topology. So as I said, in topology, we start by saying, let me classify spaces up to homeomorphisms. Then we compromise and say, let me classify them up homotopy equivalence. So homotopy equivalence is very easy to define, right? And but the thing is that what you want is, given a morphism, you want to know whether it's a homotopy equivalence or not. And the way we want to do it is perhaps by measuring some invariant, some algebraic invariant of the space, and just check if that works, right? So the natural thing to do is to look at the homotopy groups. So we say that a continuous map is a weak equivalence if it induces a bijection on pi naught, which is the set of connected components of x and y, and also on the homotopy, also pi I based at little x. This is being mapped to pi I y based at f of x. This should be a group isomorphism for all I greater than 0 and all points x in the space x. So this is what we call as a weak equivalence. So it's very easy to see that. I'm not going to define what the people are familiar with this, but so just from the definition, since they are defined based on homotopy classes of maps, it is clear that if you take a homotopy equivalence, then that will be a weak equivalence. But the converse, whether it is true or not, that's a non-trivial question, right? But the point is that there is an advantage in studying weak equivalences as opposed to homotopy equivalences, because weak equivalences can be detected by using this algebraic invariant, and then you can for actually measuring, just computing pi I, and then you might be able to. It might be easier to prove that something is a weak equivalence, but to prove that something is a homotopy equivalence, you actually have to construct homotopies, which might be hard, right? So that's at least the way one can look at this. And so what we do is we would like to localize this category with respect to weakness. So then the question, of course, should arise that, well, this is a bit of compromise. So to what extent do weak equivalence and homotopy equivalences agree? So there is an answer to that. But basically, one prefers to invert weak equivalences for, well, I would say that this is one of the reasons that at least one has an algebraic, some algebraic tools for detecting weak equivalences. Okay, but so I'm just going to list out some facts. So here let W denote the set of the collection of all weak equivalences in my category of topological spaces. So then the thing is, one can show that any space is weakly equivalent to a CW complex. So this requires a little bit of work, but it's not that hard. And so we'll just we'll assume that. Now, the thing is that there's an advantage to working with CW complexes, that if X is a CW complex and Y is any space, then the morphisms from X to Y in the localization are actually represented by something in the original category. Okay, so this is for this you need that X should be a CW complex. Well, you can actually relax that condition a little bit, but not by much. But at least this kind of some insight into why CW complexes are important. And so what do you do? Well, you define what's called homotopy of two maps. When two maps are homotopic to each other, so that gives you an equivalence relation on the continuous maps from X to Y, and you just go modulo that equivalence relation, and that gives you the set of morphisms from X to Y in the localization. So now I just want you to note here that I don't care whether Y is a CW complex, right? I just want X to be the CW complex. The first space has to be the CW complex. We'll compare that with what happens later. Okay, and also two CW complexes are homotopy equivalent and only if they are weakly equivalent. So this, the upshot here is that localization is better understood if we replace each space by some weakly equivalent CW complex. See, anyway, what's going to happen is if you localize with respect to weak equivalences, then any space might as well be replaced by a CW complex, right? And then when you are studying what is happening to CW complexes, then you are basically what you're doing is involving homotopy equivalences, which is what you wanted to do. Okay, so in a way, this is a compromise based on what we said we wanted to do in the beginning, that we wanted to look at things up to homotopy equivalence. That's not what we are doing, but at least this places put something into perspective, and I think it should also clarify why CW complexes are important. So this entire mechanism is what we are interested in, that basically you are replacing your space by something else, and then you are able to actually represent your morphisms in the localization by an actual morphism. I mean, in a sense, I mean, this is exactly what happens with the calculus of fractions also, right? Basically, a morphism in the, I mean, if you have calculus of fractions, then a morphism in the localization is given by some what is you know like a roof diagram, right? That kind of thing. So basically, what that means is that you're replacing either the domain or codomain by something else, and then you are able to get a morphism. Okay, so there is another situation where this kind of thing happens. So these are called simplicial sets. So I am going to have to talk about them because they will come up later. Again, I will not give a very thorough treatment. Let's talk about firstly it a little informally. So roughly speaking, what is a simplicial set? So it with how to put together a topological space by gluing together n-dimensional simplices along their faces. So like polyhedrons and things like that you can build them by putting together simplices, but you don't want to glue them together arbitrarily. Like CW complexes are glued together with a lot of flexibility. What you want to do here is that two n simplices, if you are gluing them together, they have to be glued together along a particular face, right? With that kind of gluing, whatever you can make, that's so that kind of topological space. Well, we are not really interested in the topological space because, see, the thing is that the idea here is that the space is not that important because we are. It's what matters is that how you put the pieces together. So if you just look at the data for how you put the simplices together, then essentially you can capture whatever is happening in the space. So then what we do is forget about the space and focus on the data. Okay, so this data about how you're gluing things together. And another thing I want to say is that the simplices are supposed to be oriented. So that's why I've drawn these pictures. I don't know how helpful they are, but so for example, this is supposed to be a hollow triangle, but then all the edges have a certain direction to them. And similarly, this then I have drawn a triangle which is supposed to have, it's supposed to include the interior. So all the edges have certain thing, and I've also put a certain orientation on the interior. So practically, I mean, what that really means is that basically the vertices of the simplex are ordered. You fix a certain orientation. That's all we are talking about. Okay, so now I will talk about what this means formally. So more formally, what a simplicial set is it basically consists of the following data. So as I said, it's basically data for putting together, gluing together simplices to form a topological space. So what you should do, firstly, you should start with your collection of simplices. So Xn is going to be your collection of n simplices. Okay. And then what you want to say, okay, so I have got n simplices, I've got n minus 1 simplices. Now what I want to do is I want to identify some of these n minus 1 simplices as being faces of the n simplices. So there are going to be face maps going from Xn to Xn minus 1. Now an n simplex will, so if I look at, let's say a 3-dimensional simplex, that's a tetrahedron, then it has got 4 faces, right? So basically I need 4 face maps going from X3 to X2. So more generally, for any n greater than 0, I have got these face maps indexed from 0 to n going from Xn to Xn minus 1. So this is telling you which n minus 1 simplex is the ith face of which n simplex, and so on. But you also have maps going the other way called degeneracy maps. So the idea is that any n simplex can also be viewed as a degenerate n plus 1 simplex, which just happens to be flat. Okay, it's flattened out, which means, so what you do is that, for example, how would you view a segment, a line segment as a triangle? Well, you just say that 2 of the vertices occur at the same point, right? 2 of the vertices are actually coincident. So basically, you want to repeat some vertex, right? So by repeating, for example, similarly in a triangle, if you repeat some vertex, you could view it as a tetrahedron, right? So the thing is that, so in this manner, you can say which vertex you want to repeat. And then from that perspective, you in which way you are viewing your n simplex as an n+1 simplex. These are the so-called degeneracy maps. So these are also important, but maybe geometrically a little less appealing. But anyway, so this is the data that you need to put things together, right? This data is telling you how your topological space is being put together from simplices. But as I said, we are not interested so much in the topological space as such. We are going to focus, our main object is this data. Okay. And so this data is supposed to, I mean, these maps are supposed to satisfy certain properties to make sure that everything works out well. So I have just listed out these identities. It's not important that we read them, but I just wanted to show what they're like. But I've said, just ignore this for now. I mean, we don't need this at all in these talks. But we should just be aware that there are some identities like this. So actually, one way of describing this object is basically you can describe it as a functor from a certain category into the category of sets. Because see, for every integer n, I'm picking out certain set xn. Right. So basically what you would do is start with a category whose objects are 0, 1, 2, 3 up to and you know, all positive non-negative integers. And then in that category, you need to have certain morphisms which will satisfy you know, this kind of these identities. And so it's you know, you can read this up. I don't want to spend time on it, but I'm just saying that you can define all this as a functor. That's actually the more elegant way of doing it. But anyway, so now that I have got all this data, can I do some geometry with it? So yeah, you can do geometry with it because it is supposed to be a geometrical object to begin with. So what you can do is, as I said, this is meant to be a recipe for constructing a topological space. So how do you construct the topological space? For every element of xn, you take a copy of an n-dimensional simplex. Okay, then you glue them together using the face map by interpreting di. So if sigma is my n simplex, I the ith face of the n simplex, and then you know I'll ask you to believe me that you can do this, and this allows you to construct a space as expected. So this space that we construct, this is called the geometric realization of the simplicial set. So I'm writing my simplicial set as X with a dot below it. The dot is supposed to tell you that, you know, it's basically for every n, I have got n simplices. And then you put this these bars around it to indicate the geometric realization. So the geometric realization is the topological space that you construct according to the recipe that is given to you by the simplicial set. So now, what is a morphism of simplicial sets? Morphism is a collection of functions. So for every n, I have a map, I have a function going from xn to yn, and these should be well behaved with respect to the face and degeneracy maps. So if you know, if you look at the definition where you define simplicial sets as a functor, then these would be the natural transformations. Okay, but anyway, I will leave it to you to read up on that. So this is your so okay, now that if you have so if you take a morphism of simplicial sets, we say that this is a weak equivalence if the induced map on the geometric realizations is a weak equivalence, as a weak equivalence of topological spaces. And so of course what that means that is that you will want to calculate the homotopy groups of the geometric realization, and these are what we will call as the homotopy groups of your simplicial set. So what I do is, firstly, the set of connected components that is straightforward. There I don't need a base point, but for a simplicial set, to choose a base point, I just pick something that is there in the in x0, right? And that's a 0 simplex. That's my base point, and so that gives you a point in the geometric realization, right? So you just calculate the homotopy groups based over there, right? So this way you are able to define homotopy groups for simplicial sets. Okay, and now, so this is the category. So I will write the category of simplicial sets as S set, and W is the collection of weak equivalences in this set, in this sense. And I want to understand W, the localization of the category of simplicial sets with respect to weak equivalences. And so this situation is very similar to what we have done with topological spaces. Again, the question is the same. We need certain for understanding the localization. So here's what we do. Firstly, we can talk about homotopies in this context also, because firstly, you can define a product of simplicial sets in. So I'm not writing it out explicitly, but it's sort of done in the obvious way. You also have the correct, you also have candidates to use for the unit interval, basically the one-dimensional simplex, which has got basically two vertices and a single edge between them. That would be your one simplex. That would be what you will use to define homotopies. So I'm not defining what the standard simplicial sets are, but I will just draw some picture. So, a one simplex is basically something that looks, I think this is not visible. So, but anyway, so it's basically just a segment, and delta 2 would be a triangle with a single two-dimensional simplex and so on. So, of course, well, I mean, I'm not being very precise here, but anyway, I hope you understand what I mean. And so then you can define a homotopy as a morphism from X cross delta 1 to Y. Right? This is a homotopy of X, of maps of X into Y. So then, just like over there, we had CW complexes. Here we study something called Kahn complexes. So I'm not going to explicitly explain what Kahn complexes are, but I will just say how they fit into this picture. So one thing is that every space is weakly equivalent to some Kahn complex, and in fact you can do this functorially. So there exists a functor. So yeah, is there some way I can actually hide this thing? Because I think yeah, okay, yeah, this is better. So yeah, so there is a functor from simplicial sets, from the category of simplicial sets to itself. So what this functor is supposed to do is, given any simplicial set, it's supposed to construct a Kahn complex which is weakly equivalent to that. Okay. Not only will it be weakly equivalent, but the weak equivalence going from your simplicial set to the Kahn complex, this also is functorially chosen. So there is a natural transformation from the identity functor to X, such that X for any simplicial set X to well, I'm saying X now, but so basically the Kahn complex constructed from X, this is a weak equivalence, and okay, so that's basically the idea, right? So you have a functorial way of replacing every object by a Kahn complex, a weakly equivalent Kahn complex. Now, how does, again, so what was the point of this? That just like in topological spaces, we could replace every topological space by a weakly equivalent CW complex, and this helped us compute homotopy, compute morphisms in the localization. Similar here, that if X is any simplicial set and Y is a Kahn complex, then the morphisms from X to Y in the localization, these are actually represented by morphisms in the category of simplicial sets going from X to Y modulo homotopy equivalence, modulo homotopy, right? So, so now the only thing you should notice here is that when I talked about topological spaces, I replaced the first space by a CW complex, right? Here I'm replacing the second space by a Kahn complex, and there is a reason for this. So we will put all this together. And again, but you do have a similar statement here that if X and Y are both Kahn complexes, they are homotopic if and only if they are weakly equivalent. So again, in this situation also, you see that if you have a mechanism to replace your object by a nicer object, then the localization becomes easier to study. Okay, so yeah, so I know I have not really even defined what a Kahn complex is, but I mean, that's more or less what these lectures are going to be like. The idea is just to convey, the grand plan of things. So basically what model categories are is that, you want to generalize these two examples. There are other situations also where they are applicable. For example, the construction of derived categories that could also be put into the formalism of model categories. Anyway, so I will just focus on these two examples. So the idea is that tools are being used over there. We want to generalize them and make it into a abstract formalism. So I'm not going to give a complete definition. So I'm putting that as a warning that I'm not going to give you a complete definition. It's not that the complete definition is hard to give. It could fit into a slide and a half, but it wouldn't really matter. But I'm just going to say that a model category is a category with some extra structure, and I'm going to look at part of the structure. Okay, so what other structure does it include? So firstly, there should be a class of morphisms which you want to call as weak equivalences. Okay, so these are the guys that you want to invert. You want to compute the localization with respect to this class. Then also you would like to have all small limits and co-limits. So in particular, there should be an initial object, which means that from that object, there is a unique map from into every other object, and there's also a final object. So I'm choosing this notation, which is quite commonly used. For the initial object, I use phi because phi is the initial object in the category of sets. So here we are not talking about the category of sets, but still this is a good symbol for an initial object. And similarly, in the category of sets, a singleton would be a final object. This would also work in the category of topological spaces. Okay, so these are the and you also have a class of morphisms called co-fibrations and fibrations. So maybe in a later lecture, we might quickly talk about what co-fibrations and fibrations mean in the context of topological spaces, but right now I don't want to. But so an object is co-fibrant if the unique map from the initial object to X is the co-fibration. Okay, so that's so this is basically what a cofibrant object. That's supposed to be like your CW complex. So CW complexes are the cofibrant objects. Well, they are not all the cofibrant objects, but they are some of the cofibrant objects in the category of topological spaces. And similarly, so there's something called fibrations, some class of maps called fibrations. And we say an object is fibrant, X is fibrant, if the map from X to the final object, this is a fibration. Okay, so this is basically, this is not telling you anything really, but I'm just saying that there is some mechanism like this that we want to generalize. And not only, so now that we have this notion of cofibrant and fibrant objects, so just like we saw with the category of simplicial sets, you have a functorial way of replacing simplicial set by a weakly equivalent Kahn complex. So you want to have similar things. So basically there should be a cofibrant replacement functor and there should be a fibrant replacement functor. So the cofibrant replacement functor I'm denoting by C, and there is a natural transformation from C to the identity functor, meaning that for every functor, every object, I want to create a weakly equivalent cofibrant object, and there should be a functorial choice of a weak equivalence going from the cofibrant approximation into my original object. Okay, so basically I'm approximating it on the left in a certain sense. Okay, so basically, okay, and similarly, I have a fibrant approximation functor, which means that I have a way to replace every object by a weakly equivalent fibrant object. But now there should be a map going from my original object into the fibrant approximation. So I have a natural transformation from the identity functor to the fibrant approximation functor. Okay, so this is that we have. This is not a complete definition simply because I have not even said what what cofibrations and fibrations are, or at least what kind of properties they're supposed to have. That's why this definition is not complete, but that's okay. You can just look it up in a book. And the thing is that I'm also going to say without much clarification that you can define a notion of homotopy in a model category with the right. So I think there have been some lectures on homotopy theory, and I think at some point you have defined homotopies, right? So basically using that kind of, I didn't really look at those lectures, but I just glanced at it, and the correct ideas have been discussed there. So you can define a notion of homotopy in the in the notion of, in the context of model categories. I will, maybe I will clarify a little bit on this in a later lecture. But anyway, so now that you have some, all this mechanism, then we can talk about the model category with respect to weak equivalences. And this is called the homotopy category of your model category. Okay, and this now this has this nice, I mean, the way this works is as follows, that for objects X and Y of the model category, the morphisms from X to Y in the localization, in the homotopy category, how do you get them? You replace X by a cofibrant approximation, you replace Y by a fibrant approximation, and you take the morphisms from this, from CX to FY, and then you go modular homotopy. Okay, so that's how the whole thing fits together. And in topological spaces, any space is fibrant, but not all spaces are cofibrant, but CW complexes are cofibrant. So these are not all of them. There is a more general notion called cell complexes that one can define, and those are, and then basically any object that is a retract of a cell complex would be cofibrant, and so on. So these are not all the cofibrant objects, but there are some of them. And in simplicial sets, any object is cofibrant, at least if you choose a certain model structure. And fibrant objects are the Kahn complexes. Okay, so that's it. It is in this sense that this this notion generalizes what we see in the category of topological spaces and the category of simplicial sets. Okay, so now that we have all this, let us go back to algebraic geometry and talk a little bit about this, about where we are going to use this. So I need to set up the context. So what I do is I fix some base scheme, which should be a finite dimensional Noetherian scheme. So I think it would be fine if you just take S to be the spectrum of a field. And then we look at the category of, so SM over S. This is the category of finite type smooth schemes. Okay, actually I should have said over S. Finite time smooth schemes over S. So I'm not saying that it is the morphism from the scheme to S is smooth. I'm just saying the smooth scheme itself is smooth. Okay, that's actually important. So I'm talking about smooth schemes over S, not schemes which are smooth over X, over S. Okay, anyway. And then we will use the Nisnevitch topology on this. So I will define what the Nisnevitch topology is. So I think you have seen a little bit of sheaves and sheaf cohomology. So, but perhaps you have not seen this topology. Yeah, I mean, should I assume what Ital topology is? Yeah, I mean, has that been talked about? Have growth-centric topologies been talked about? Okay, maybe, okay, that's fine. So basically, well, you have talked about what is, what is sheaf cohomology, or I suppose over the Zariski topology or something like that, right? So the thing is, there is a slight generalization of the notion of topology. So what is topology? Basically, given any set, given any space, you want to see it being covered by open things, right? So now what you're saying is that you have got these, so you can see the open subspaces as spaces in their own right, and you're looking at morphisms from those open spaces into your original space, right? And what is the requirement? That they should be open immersions, right? In the context of algebraic topology, you require that should be open immersions, or you can make sense of that even in the context of topology. Now, you might want to relax this a little bit, that you don't necessarily want it to be an inclusion. It could be a somewhat different map. So for example, and then you can try to define sheaves using that. And so this gives you the notion of a growth-centric topology. So basically where you define a kind of open cover where the map from the open piece into your space is not necessarily injective. Okay, but it has to satisfy a certain formal properties. So I mean, I think it wouldn't really make sense. I don't want to actually define a growth-centric topology right now, but you can just believe me that such a thing can be done, and you can just look up the definition, which is not very hard to see. But anyway, so then I should maybe explain some of these terms. So for example, what kind of thing would you want to use for a cover? So there is something called, so basically there's something called the Ital topology. So the reason why we have something like this is that, see, in algebraic geometry, we use the Zariski topology, which is extremely coarse, right? Basically what is, the open sets are actually, all the open sets that you're using are actually they're very large, they're dense, right? At least in an irreducible space. So the kind of thing that doesn't hold, for example, is that what you see in differential topology, what you can do is, when you look at a map, you can look at its derivative. And if the derivative, so if let's say you have got two-dimensional manifolds and you take a smooth map between them, then if the derivative at a particular point happens to be invertible, then what you get is a local isomorphism, right? This is very nice, but this is not true when you're working with the Zariski topology, right? Because the Zariski topology is just is too coarse. So then what we can do is we can say, let us just focus on these maps where the they're basically maps between two equal dimension, two varieties of the same dimension, and such that at every point it is inducing an isomorphism of tangent spaces. Okay, so such a thing, roughly speaking, is what is called an. So it is what you would like to be a local isomorphism, but isn't. And so then what you do is you pretend that it is a local isomorphism, and you build a kind of topology out of that. Okay, so it's not really a topology; it's something that works like a topology, and so this is what this is a Grothendieck topology. So, but anyway, so what if I take a space, an Ital cover of the space would be a covering of my, so basically a collection of maps which such that their images cover my entire space, and the maps are all Ital at every point. They're inducing an isomorphism of tangent spaces. Okay, so this is an Ital cover. So a Nisnevitch cover is a further is a stronger version of that. So see, if I take an Ital cover, so what would be an example? Let's see, what would be an example of an Ital map? So if you take, for example, the parabola y equal to x square, okay, just the graph of the function x square, and you project it onto the x-axis, then you can see that this is going to be Ital, right? As a manifold, I mean, if this is a curve and they're both curves, at each point, basically it's inducing an isomorphism of the tangent space. So this is Ital. But now notice that if I take a rational point, well, actually, maybe this was a bad idea. Maybe, let's not look at this one. Let's look at not y equal to x square, y square equal to x. Okay, so basically the horizontal parabola. Okay, but I want to leave out, now this is not going to be Ital at the origin, right? So there, it's not inducing an isomorphism on tangent spaces, but but if you remove the origin, if you leave out the origin, at every other point, the projection map is inducing an isomorphism of tangent spaces. Now notice what is happening over here. If I take the a rational point, let's take the point 2 on the x-axis. So what sits above that is going to be the point 2 comma root 2. Okay, so it's not a rational point. Okay, so basically, if you go upstairs, you don't get a point with in the same with coordinates in the same field as before. You have to go to some algebraic extension. Okay, so this is something that can happen when you are working with an Ital cover, that every so every point is covered by something, and this is inducing an isomorphism of tangent spaces in a certain sense. But what is happening is that the point upstairs is not defined over my original field. It's defined over something else. Okay, so if we say that, no, I don't want this, I actually want that point upstairs to also be defined over the same field, meaning that in the in a more rigorous language, what I'm saying is that the residue field at both these points should be the same. Okay, then we say that this is a Nisnevitch cover. Okay, so so I will talk about, I'm just defining something right now. So next time I will actually talk more about why the Nisnevitch topology matters and how, what it really means. Right now, I'm just trying to get to the end of this thing. So just the end of the definition, so that then we can, and then we will sort it out later. So, but anyway, we will come back to this definition again. But So that this is what it means for now, that for this is an ethyl cover, such that for any point X of U, there is some point Y of V such that Y is mapping to X, and the residue points and the induced map on the residue fields is an isomorphism. So this topology is finer than the Zariski topology, but it is coarser than the ethyl topology, because every Zariski cover is going to be a Nisnevitch cover, but every ethyl and every Nisnevitch cover is also an ethyl cover, but every ethyl cover will not be a Nisnevitch cover. Now, see, if you've, since you have seen some lectures on sheaf cohomology, so you have talked about the notion of the stock of a sheaf at a point, or more generally of a pre-sheaf at a point. So here also we can do a similar thing, but here we do not want to use open neighborhoods, right? We want to use Nisnevitch neighborhoods. So given a point, given a scheme X and a point little x on X, what is the Nisnevitch neighborhood of X? It is an ethyl morphism such that this X can be lifted. Okay, such that there exists some Y mapping to X with, where this induces an isomorphism on the residue fields, but I don't care about the other points. Okay, this is a Nisnevitch neighborhood of X, not of the other points. So it's at other points it may just be ethyl, but only X can be lifted. Okay, so this is a Nisnevitch neighborhood of X, and so this is the picture that basically V to X is ethyl, and I have spec Kx is being mapped into X via X. That's the point X, and this can be lifted as a point Y of V. So then, if I have a pre-sheaf on this category of smooth schemes over S, I can define the stock of F at the point X. See, so basically what I'm doing is, in my entire site on the category of smooth schemes over S, I'm picking out one particular variety. On that variety, I'm picking out one particular point, and over that, I'm going to vary my Nisnevitch neighborhoods. Okay, and so I can define the stock in the usual way. Just take the inverse image V, where V ranges over the Nisnevitch neighborhoods of X. And then it's a fact that, so just like with the Zariski topology, you can actually compare two sheaves. Two sheaves are the same. A morphism between two sheaves is an isomorphism. If it's inducing an isomorphism on the stocks, a similar thing happens over here. That basically isomorphisms can be detected by just checking what is happening at stocks. So this doesn't happen for every topology. So every growth-index topology. So for this particular topology, it is happening that basically morphisms of isomorphisms can be detected by what is happening at something called stocks. Okay. So now we are able to talk about. Now we'll finally get to our main object of study. So the category of spaces over S. This is the category of Nisnevitch sheaves with values in the category of simplicial sets. Okay. So basically, for every scheme, I'm associating a simplicial set to it. Okay. Okay. So I think this will become clearer as we go along. So for now, let's just say that these are Nisnevitch sheaves with values in this category of simplicial sets. And a morphism in this is a local weak equivalence if it is a weak equivalence on stocks. So my objects are going to be sheaves with values in the category of simplicial sets. So every stock is going to be a simplicial set. Okay. And then if a morphism is inducing a weak equivalence of simplicial sets, I say that this is a local weak equivalence. Okay. And now the point is that there is a model structure on this category of spaces in which the weak equivalences are these local weak equivalences, and the co-fibrations are going to be monomorphisms. And this is called the local injective model structure. So all these details are not really that important. The point that you should just remember here is that I'm going to take this category of sheaves over this category, and I want to invert it with respect to local weak equivalences. So the co-fibrations and so on, that's kind of extra machinery that's just necessary if you want to get to the details. But the main point is that local weak equivalences are what we are interested in. Okay. And so firstly, I mean, what does this have to do with the geometry? I mean, how should you understand this geometrically? So in algebraic geometry, one thing is that given a scheme, scheme by itself, right? The main point is that we actually want to understand the functor that it represents, right? The pre-sheaf that it represents, which means what? That given a scheme X, I want to map all possible other schemes into that, right? And that gives me a pre-sheaf on the category of schemes. So what I mean here is that suppose X is a smooth scheme in this category. So it doesn't have to be smooth. I mean, this is something we do in general. Then let Hx be the sheaf represented by X. That is, Hx of Y is the morphisms from Y to X. So these are what we call as the points of the Y valued points of X, right? So the thing is that so what we normally do is we don't distinguish between the scheme X and the pre-sheaf or sheaf Hx, right? I mean, in algebraic geometry, we move back and forth between these two notions. So what is this really doing? So the kind of the sheaf that we are studying, what it is doing is that for every Y, it is giving you the set of Y valued points of that sheaf, right? So now what we are going to do is now our sheaves are simplicial set. They have values in simplicial sets. So given a space, the Y valued points of that space, they do not form a set. They form a simplicial set. Okay, so there is a certain extra geometry within the collection of points over some Y. But so every object X, this anyway, I mean, by our usual definition, it represents some pre-sheaf which takes values in the category of sets. Now, the thing is, every set can be viewed as a simplicial set, right? Basically, just as a discrete, roughly speaking. Or in other words, what you're doing is you're taking the constant simplicial set. So if S is your set, then you just set Sn equal to S, and all the face and degeneracy maps as being just the identity map. So that roughly, I mean, what this means is that you're just viewing your set as a discrete topological space, right? So this allows you to see every set as a simplicial set, and so in particular, every sheaf with values in of sets is also a simplicial sheaf. Okay, and so we have this functor going from which take maps X to Hx, which is an embedding of my original category into the category of spaces. And the fact that it is an embedding actually comes from this statement that if you look at the natural transformations from Hx to F, so if F is some space, which means it's a sheaf, which means it's basically a functor, then if you look at the natural transformations from Hx to F, that is just given by F of X. Okay, so so this is I mean, I'm sweeping a lot of stuff under the rug over here because I mean, here I'm saying Fx is actually a topology, it's a simplicial set, right? But on the left, what I have is not, I mean, I'm just looking at morphisms, which potentially would be just a set, right? But the point is that you can make it into a simplicial set also. So I'm not talking about that right now, but the point is that there is a kind of a simplicial version of the Yoneda lemma. Okay, that's what you should. So one thing I should say is that, see, this business about simplicial set is kind of optional. That I could have just not talked about simplicial sets, and I could have just said that I don't want to talk about, I want to talk about Nisnevitch sheaves of topological spaces. So the thing is that anyway, simplicial sets are just a way of combinatorially representing topological spaces. So instead of talking about simplicial sets, I could have just talked about topological sheaves. Okay, sheaves of topological spaces over everything, over this category of smooth schemes over S. And so what I'm saying over here is that when I take morphisms from Hx to F, I wanted to have a topological structure also, which is perhaps a bit more believable that you can do such a thing. Anyway, so there is basically, I mean, if you're familiar with the Yoneda lemma, then there is a simplicial version of the Yoneda lemma. And that gives you this, and it allows you to view every scheme as being actually a space in this sense. So now, yeah, I'm just about to wind up my definition, with which will perhaps not say a lot, but it's something for us to build on. So now, why model categories? So the thing is that model categories, naturally they have a certain mechanism for which can be used for localization. So let M be a model category and A be a set of morphisms in M. Okay. So my point is that I already have inverted weak equivalences. I want to invert a few more things, let's say. Okay. So then, under some conditions, which we will not necessarily specify, there exists a new model structure on M such that even this set A becomes weak equivalences. So any old weak equivalence remains in the new structure. Also, every element of A also becomes a weak equivalence. The cofibrations remain unchanged. And the new model structure that you have is somehow universal with respect to these requirements. So just like when you construct the localization of a category, you don't change. I mean, one of the ways of saying it is that you don't change the objects, you just change the morphisms. And this has a certain universal property that basically, if you take any functor which maps your category, which from your category into some other category where these morphisms are becoming isomorphisms, then that functor has to factor through the localization. So in that sense, there is a universal property that this thing also has. So this is called the left Bousfield localization of M with respect to A. So basically what I'm saying, the summary here is simply that there is a model category version of localization. You have seen localization of categories. There's a model category version of that, which is, again, I have not defined anything and I have not even said under what situations this happens. But the point is that there is a machinery to make all this workable. And so then the idea is that we take this category of spaces that we have and we localize it with respect to morphisms of the form F cross A1 to F, the projection, which is the projection map on the first coordinate. So this is what we started with. We said that these are the guys we want to invert. Okay. So this model structure on the category of spaces is called the A1 homotopy model structure. And then the corresponding homotopy category of this for this model structure is called the A1 homotopy category. So, so that's basically the definition, which is again not saying much, but at least now I hope that you can see what is supposed to go into it. So what we want to do next is maybe see a few more details. So firstly, why the Nisnevitch topology? What makes it tick? And yeah, maybe a few more definitions. Like, for example, there is a notion of homotopy groups for topological spaces. We want to look at corresponding things over here. So that's basically, I'll be filling in those details and maybe discussing this in a more leisurely manner in the next talk. I suppose, I mean, one of the things I would like to do, as I said, is provide some kind of a list of reading suggestions for this. I have not prepared it with this talk, but I would say that if you plan on following these talks, then if you are not familiar with the notion of a growth-ending topology, it would be best if you look into that before the next talk. And I mean, you don't have to read a lot about it. Just for example, something in the what is given in Mill's book on Ital homology or something like that. Or there are many other resources for this. Any place where you just see the definition of growth-ending topology, if you just go through that, that will be good enough. Okay, so I'll stop here.
Okay, thanks, Professor. So we see you next week at the same time. We'll upload all the necessary resources in the website. So stay tuned. Okay, goodbye.